Welcome, everyone, to a new episode of Your Friendly Physicist and Other Nerds. I'm Lucas, the host of this podcast, and today I'm speaking with Brian Pauw, who is a researcher at the Bundesanstalt für Materialforschung and Prüfung in Berlin. And there he runs an X-ray scattering machine called the MOUSE instrument. And if you're interested in adding X-ray scattering to your science project, but you have no idea how, or you need a really good instrument, or option 3, you have a very complex system that needs, let's say, expert processing and analysis, then you can give Brian a call and discuss further options. Or you simply have a look at his science blog, lookingatnothing.com, where you find a lot more information about Brian and the MOUSE instrument. I'm following Brian on his blog since a couple of years now, and recently we met at a conference about small angle scattering in Taipei, where I asked him if he wants to join the show and talk a bit about small angle scattering. He immediately agreed, which made me really happy, as I'm fully aware that small angle scattering is a super nerdy topic, but if someone can make it interesting and exciting, then it is Brian. There's a lot of proof about this on YouTube, where he uploaded some of his talks. On YouTube, you find him as Dr. Head Damage. A short disclaimer before we jump right into it. We do not talk exclusively about small angle scattering. After roughly half of the episode, we slowly drift away and talk about all kinds of stuff that is important to Brian, but also to me. Science communication, the dark side of academia, advices for young scientists, how to fight the inner imposter, and a lot more. That wasn't really planned, but I'm very happy how this turned out. So, Brian, you have worked in many places, the Netherlands, Denmark, Japan, now in Germany. Please correct me if I forgot anything. Together with many different people, but I would say you have always been loyal, can call it loyal, to small angle scattering. Can you briefly explain the concept of small angle scattering? Why do we need small angles? And what is the cool thing about scattering?
Yeah, it's been a while. I've actually gone through a couple of stages in my career. First, I was interested in analytical chemistry, and then after a couple of months, I got bored with that. And then I thought, okay, well, maybe I want to do something with computers. So then I started a master's project on computational chemistry. And then I spent like 6-7 months just behind my computer throughout the summer time. And I thought, okay, well, this is also not it, right? I don't want to, I need something which has something to do with computers and something to do with, but some practical bits as well. So I remember the company internship that I did at Teijin, where they gave me this incredibly ancient small angle scattering machine to work with. So that was that was good fun, because you screw around with the machine, and you get this weird data that somehow tells you something about the fine structure of the material. And there's no handholds on this, right? So the data looks absolutely, yeah, it's like a sort of smooth curve, and somehow that tells you about what kind of pore structure you have in your material, or what kind of nanoparticles you have, or something like that. And it's up to you to make the link between, okay, between that data and what you actually want to know. So I found that quite interesting back then. So I thought, okay, I'll do a PhD project about that. And there you find out that this field of small angle scattering is actually ancient. For the first mention of small angle scattering that I have is from something like 1915 or something. And not long after, people started experimenting with it and came up with all kinds of wild ideas. So sometimes when you do research for small angle scattering, you dive into the library, and you end up with these absolutely ancient papers that nobody has seen or nobody has read or cited, and you just find out all kinds of cool details about this. Now, the way I usually explain small angle scattering is first by finding out whether people are really asking or whether they're just being polite. I I think that's a problem that we scientists have, is sometimes when people ask us about our research, we're so But when you find out that people really want to know what it's about, you say, well, small angle scattering is a super simple technique. I mean, you shoot a beam of X-rays through a sample. The structure in that sample causes this beam to not just go straight through, but actually bend slightly. So if you put a detector far away, you see this splatter pattern on the detector, and that somehow you can calculate um, has its origin in a fine structure. So the experiment is super easy, and you can do it with lots of materials. I mean, the amount of materials that we measured on our machine spans pretty much everything that you can get your hands on. I usually stop there, and then that when people are really interested, they will ask, okay, well, but what is it good for, right? What do you use it for? What do you get out of it? And then you can go like, okay, well, for example, there's a company that produces ceramic nanoparticles. These you can measure in one of two ways. You can either do electron microscopy, which you should always do, which gives you a real image of your nanoparticles, and that's fine. But that is a slow and tedious process. So if you want something quick and if you want something over large amounts of sample, then you stick it in a small angle scattering machine and you get the same particle size distribution out for your particles with much, much less effort. And that really opens up possibilities for investigating if you change the manufacturing procedure of your particles, does that then change my particle size? Is that important? Does it affect any other material properties? You can show people that this stuff really has some practical benefits and practical applications. So
If I were not convinced yet by small angle scattering, I would be now after listening to your explanations.
yeah, it's a bit of a wild technique. I mean, yeah, as I said, it existed for such a long time, but it's only recently that we really started being able to exploit it to a much fuller degree. Over the last couple of decades, things have become a lot better in this field. And I think that has opened up the technique to a whole lot of customers and researchers that otherwise would never have looked at it. So interestingly, I was at a magnesium conference like 10 years back or something. This is already going a little bit into history, but you can make magnesium alloys, right? And they, depending on what kind of alloy you make, you produce these really fine structures inside your magnesium, which change the strength of the magnesium alloy or the ductility. Or anyway, at this conference, people were only showing results of electron microscopy, stuff that they measured with lots of effort and lots of tedium. And I was the only one who showed small angle scattering results there. People came to me and said, "Oh, I never knew you could do this with small angle scattering, that you could get particle size distributions of volume fractions, exactly the things which are so hard to get with electron microscopy." But the thing is, this is how small angle scattering started. So in 1930, Guinea, one of the first people to actually apply small angle scattering to a material, used it to find out more about the fine structure of metal alloys. That's where the name Guinea-Preston zones come from, that you hear everywhere in electron microscopy. Well, Guinea was a diffractionist, Preston was a diffractionist. So these two people were actually just looking at small angle scattering to investigate metals. And then for a long period, that information was lost. And now people are rediscovering that you can actually use small angle scattering in addition to electron microscopy to get much better information from your samples.
Yeah, I really like the historical perspective you're adding to this subject. It was you, right, who gave this the history of X-ray scattering on YouTube.
Yes.
This is one of the talks I always show to my students.
Okay.
So to get a historical hang on this, because if you're new to the field of small angle scattering, it's super overwhelming. Because you have, I mean, X-ray scattering, neutron scattering, light scattering, electron scattering, whatever. Then you have different form factors, structure factors, models, super complicated samples, different sizes, different shapes, different orientations, different crystallinity. And I mean, I don't have to tell you, but how to get started with this and it always helps, or me, it helped a lot to say, hey, let's go back to the start, where it all started, 1915, and then
Mhm.
10 years, and let's see how this evolves and
Yeah,
what people
yeah.
knew back then, slowly adding information, improvements, developments, and now we are here. At least for me, it was super important to have this historical timeline to see, okay, how all of this evolved, and now we're here, and now I have a better understanding what this technique can do, but also what it cannot do. When you
Mm.
always see this, overfitting of data or over interpretation of data.
Yeah, I mean, it's it helps it helps to add a bit of a practical side to that as well, so that you can show that,
Hmm.
look, this is really, it's actually stupidly easy to do.
Yeah.
It's very hard to do right, but to do the experiment and so on, that's super easy. Um, and yeah, the history I think also tells us a lot, but it tells us that people have made a lot of improvements over the years, some of which never worked. Right. So I've read papers with machines that you never hear about again. So obviously that didn't work. And actually contacted a few of these people when I was writing a review paper, and I said, look, I read about this machine, but then I
Hmm.
didn't see anything about it. So did this work? And they
Hmm.
said, yeah, it kind of worked, but we don't recommend it ever to anyone ever again because it's just so annoying. So yeah, that was good fun. But you brought up the point of saying what you can and moreover cannot do. And that is, I think, where we lose most of the people, because every time a person comes to me that doesn't quite know about small angle scattering, and comes to me with their sample and say, can you measure this? My usual answer is, well, that depends, because there's like four or five, six different things that play a part in figuring out whether something works or doesn't work. And when you try to explain this to people, they immediately go like, okay, well, I'll just go to microscopy then, because let's just stick it in and see something, right?
Yeah, a real image.
Yeah,
Yeah.
exactly. I think we have to be a little bit careful about how we introduce new people to the technique. And this is also why we run the lab the way we do, right? So
Mhm.
we don't let people measure on the machines themselves. We don't let them struggle with the data correction or with the analysis and so on. Because those are things which have so many pitfalls. There's so many ways of doing it wrong, which
Yeah.
we've learned the hard way over the last 15, 20 years, right? And you don't want people to have to fall into each of these
Yeah.
pitfalls themselves before they get a decent answer out. So we do everything. We sit together with them, and first we have a discussion about, what is it? We show them the machine and show them sort of what kind of results you can get out. We try and understand what their samples are. We recommend what they should bring, extra samples to bring. They're always afraid that they bring too many samples. You can never have too many
Hmm.
samples. You can bring, I mean, we've done this project where we synthesized 1,200 samples. That is maybe too much, right? That's
You me
I'm
you me you measured all of them?
No, I'm at sample 700 or something at the moment.
Wow.
We measure them in
Hmm.
between other runs, but if you bring like four samples, I would rather you bring 15 samples or 20 samples,
Hmm.
because you get a much better idea about your material and what everything means if you do that, rather than four samples. Four samples is like stabbing in the dark. It's like, yeah, there's difference between curves. Is it significant? Is it systematic? I don't know,
Yeah.
right? So bring me a very nice series, and then we can work from there. So basically, by hand holding them through the first experiment, you can get them excited about the
Hmm.
data and about the analysis, and they can start to understand gradually what it is that they're getting from the data,
Hmm.
what it is that you cannot get from the data, and where you need extra information. So yeah, I mean, all the techniques that measure in this sort of size range, they all have their limitations, and they all have their artifacts, and they all have their asterisks when it comes to interpreting the data. And it's
Yeah.
super important to tell people that, look, this is limited information, and You need to
Yeah.
combine it with the other techniques. There's no other way around it. You cannot just do this one technique and assume that you get your protein shape out of it just out of the blue, right?
From all the things you just said, what would be the one thing that you would wish that people would know about small angle scattering?
That you should start the experiments at an early stage and take your time for it, or at least allow time for it, because the measurements don't really take that long. The data processing now doesn't take that long either, but developing a good analysis model for your particular sample, for your particular structure, that takes a lot of time. And not because you spend a lot of time coding or whatever. No, you spend a lot of time sitting and thinking thinking again about how you would approach this particular problem. How complex you want to make your model. Do I want to go for something relatively generic so I can get some sizes out? Is that maybe enough? Or do I really need a very custom model that describes each of the features in the data and gets a lot of information out, but is only for this particular sample type or sample series? And that requires some discussions with the users and requires them to get maybe some extra information, or to think about things, or yeah. It is a process. It's not like a UV-vis spectrometer or something where you put in your sample, you push a button, and 5 minutes later you have some curve. So yeah, it's a bit more involved, but the things that it lets you do are worth it for most samples. Just the fact that you can put your sample in, and you can measure it fine, but you can also heat up your sample. You can pull on your sample. You can apply an electric or magnetic field and see how your sample responds to that. You can
endless possibilities.
Exactly. And all of that gives you a good insight in what your material is and how it behaves and what it does and how you should improve your material.
It also gives you very good prioritizing skills, because there's so much you can do that you have to decide: are we going for temperature? Are we going for pressure? Are we going for magnetic field?
Yes. And I'm traditionally very, very bad at this prioritization, right? Because I like to do everything perfectly, and that is a problem because I only have a limited amount of time. And
But if anyone deserves to do everything, then I would say it would be you, because you set up this mouse instrument in this fantastic lab environment.
yeah, I mean, initially I wanted to build the machine myself as well. And I budgeted for that, but I'm actually grateful to my line manager, who said, "Look, don't do that. Buy yourself an instrument which is already ready and running, and which you can start with, and then you can modify it, and that's fine. But don't build your own instrument from scratch, because it will take ages, and for a long time it will not have any output, and then people will look badly upon you because you don't have any output. So on the one hand, that is unfortunate. On the other hand, it was very good advice, because we still have been able to change the machine exactly the way we want, and to modify it to an incredible extent. But we could do so gradually. So we were producing output even as we were making these changes.
So the current state of mouse is roughly the state you wanted to be in?
Yes. We want to integrate more robotics and more automation, because measuring a sample is nice, but as I said, measuring a series of samples is even nicer, and measuring samples that change over time is super nice, right? And you can make incredible investigations by adding automation to the machine. Okay, so you can say, well, I have a material that I'm dynamically trying to optimize. I want these and these particle sizes. And then you can have your automated system generate the samples, and you measure the samples, and that informs the synthesis part, how they should do the next syntheses. And that allows you to quickly develop a material to have the properties that you want. And that is one of the reasons why we made the big changes that we made over the last month, to get away from the restrictions that were imposed by the original manufacturer, right?
Okay.
Because if you don't modify your machines, you will always measure within the constraints of the original manufacturer. So through modifications, you can go beyond the boundaries and you can do more stuff. For us, that has enabled now the ability to integrate any hardware that we want and to sequence the machine in any way that we want. So that now, it used to be able to measure for up to 3 weeks at a time for 48 samples. I hope that at some point I can leave the machine alone for half a year and that it will just continuously do something and do something useful, right?
Yeah.
So I don't know if we'll ever get there, but
Sounds great, really. Do you have an idea how many samples you have measured over the years on this
yes, we
instrument?
we have an exact idea because one of
Wow.
the things we started out with was to drive the machine by means of an electronic logbook. And this is a fancy way of saying it's an Excel sheet. We fill in the measurements in this Excel sheet, and that gets read by a Python script that turns it into a measurement script, and that's exactly how the measurements are run. So we know how many samples we measure, and we know that we're measuring something like 720, 730 samples per year.
Okay. Wow.
If we are in a good year, right, with very little downtime and so on. So this year we've had a bit more downtime. But when my colleague Glenn Smales was still working with me on the instrument, that was 720 or something. That was sort of the maximum that we would do per year. So
For how long is it running now?
about 7-8 years, I think.
Okay.
Yeah. So yeah, it's been a really good machine. I think we've used it way more than it was intended to.
Yeah, that's always good if it turns out this way.
Yeah, exactly. I was looking at how many hours the X-ray generator had run the other day, and it said 32,000 hours. I was like, oh, great! I managed to capture it in a good time. And then I came back the next day, and I was like, yeah, still on 32,000 hours. So obviously we've reached the end of the counter.
Oh, wow. It's still running.
And it's still running because yeah, it should be closer to 60,000 hours actually by now. But
Okay.
so obviously I hadn't paid attention to this for a long time. But yeah, it's been running well. But yeah, we keep good statistics on the machine, and we can see that we have, through these changes that we made, we've more than doubled the efficiency of the machine.
Amazing.
So yeah, instead of buying a new machine, you can work on the existing machine and improve it.
From all these samples and sets of samples you've measured, do you have any particular set that you really liked?
Any set that I liked? Okay, well,
Or that stood out in some way?
well, there's a set that I like because I like to show it, because it's a set where a colleague of mine was working on loading resins for 3D printing with ceramic particles. So after a couple of tries, which didn't work well, she in the end managed to create a consistent series of 15 samples or something, with gradually increasing densities of these particles in them. And when you show the data, it really nicely shows not just the increase of these particles, but also as they come closer together, you start seeing interference of particles closer together, and that really shows up nicely in the data sets. In terms of other memorable samples, well, we've measured a lot of biological organisms. We've had a squid pen recently, the backbone of a squid. We've also measured sheep's tooth with an implant in it. We've even measured human blood, or French blood, which I do not recommend to anyone, because we're using a flow-through cell, so we have like 1 meter thin tubing, and blood, by its very nature, has a tendency to coagulate and try to block any sort of flow. So getting the sample in the cell was possible, and getting it out of the cell was no longer possible after that. Plus, it's human blood, so you need to do extra safety precautions. That is a sample that I will probably not repeat.
But you got nice results out of it?
We got some interesting results out of that. We were actually looking for a particular effect which we did not see, so it never got published. But at least we got to see the hemoglobin nicely.
Mm-hmm. Cool. So talking about samples that led to nice results, what about the other side? I can imagine with these thousands, hundreds of thousands of samples, probably you have quite a lot that didn't work out in the end. I mean, how do you handle these moments?
Well, yeah, the good thing about measuring so many samples is that you always have a couple of good samples to remember. Um, we tend to stay away from actually a whole class of samples, which are liquids and suspensions in liquids. Because our machine is set up to be um, really convenient in measuring solids, um, we stay away from most liquids. The second reason for that is that the data never is as pretty as it is for sort of the dry samples. You have so many background contributions when you measure liquids. You have the glass capillary itself, which scatters, but you also have the dispersant, like water. Water has an amazing amount of scattering, which you need to subtract afterwards, and you can't increase the concentration of your analyte infinitely either. So you're always left with a very noisy signal, which, in my eyes, leaves too much room for alternative interpretations. If you really want to bring down those uncertainties on your data, then for liquids that is super hard.
Besides running the mouse instrument and this X-ray lab, you also have a science blog and a YouTube channel,
Yes.
Dr. Head Damage. Where does the name come from?
That was a joke by one of my friends when I was doing my PhD. He said, "Oh, you know what PhD stands for? Permanent head damage." But permanent head damage was too long for a YouTube handle, so I shortened it to Dr. Head Damage.
Cool. Nice
Um,
story.
yeah, I thought of changing it, but by now, people know it, and people understand that, just like email and email addresses in the old days, sometimes you're stuck with whatever you chose in the early days. It has a story, at least.
Yeah.
Yeah.
Your science blog is called Looking at Nothing, which I find perfectly fitting for what you're doing. Why did you start all of this? So why going actively into promoting your science or communicating your science?
So I started my blog already during my PhD time. So that thing is like, well, 17, 18, 19 years. The reason I started it was that I felt a little bit hampered by the traditional way of disseminating information in science. So traditionally, we're looking at like paper publications and presentations, and that's an incredibly slow process. I hate how slow it is because you write a paper and you submit it. You're happy that you submitted it, and you go off and you do something else for a couple of months, and then the reviews come back, and you're like, oh yeah, what was that paper about again? And you try to answer the reviewer comments to their satisfaction, maybe dig up some more data, do some more analysis, and so on. And you submit it again, and you're happy again, and for a couple of months, and then it comes back again, and then eventually it ggets published, and by that time you've lost all interest in it. That is incredibly inefficient. I actually only found out recently that whole peer review business is actually only something that started relatively recently in these academic publishing world. It's something from which started after the Second World War, after governments started spending money on science. They wanted to know whether the money that they spent was actually effectively used, right? Because, well, yeah, I don't know how they wanted to prove that, but they started a review process. And then in the 60s, this started to become popular in publications, in scientific journals. And from that point on, we've had this peer review system, and we've had, for better or worse, there are a lot of articles that are critical of this, that have reviewed this peer review system critically and say, okay, well, it didn't really work. It slows us down incredibly. isn't it time that we stop this experiment with peer review and just go back to, publishing stuff? So I've always been interested in alternative ways of sort of alternative outlets of information. And for me, the blog is actually great because sometimes, I'm very easily distracted. I do like 100 different things. But sometimes I do a small investigation, just just to find out one thing, and writing that out in a blog post is super easy because it's a single topic. I just need a few paragraphs to explain what I did, why I did it, and what the outcome was. And then you can publish it on your blog, and then you can forget about it. And the next time you actually have to write a paper, you can look through your blog post and go like, oh yeah, well, here's a piece, and there's a piece, and there's an investigation, and that's something I found out. So if you look at one of our last publications on the mouse project, this is an absolute behemoth of a paper, right? It's 50 pages long. 2/3 of it, I think, are appendices, and these are straight up copies of blog posts, or reworked blog posts, because in order for me to make the main story, I actually needed to refer to some of the other investigations that I've done, and they go into the appendices. And I really like that paper. Now, some people say it should have been a book, but I like that paper because it harkens back to the old days where you would really have the time to write a decent publication in a normal tone of voice, which explains normally how you achieved something, how you did something. None of this condensed, super heavy jargon papers that only span 3 pages, where there's no methodology because that's in the supplementary information somewhere hidden away. No graphs or no data fitting results, right? All of that hides the actual effort that goes into that went into work, and just tries to oversell the results as something that it never really was meant to be. So for these sort of alternative outlets, I started a weblog, and I've thought many times of stopping it because it does take a bit of time. Some people are not too happy that I'm spending time on this and not on traditional publications, but every time I go to a conference, for example, people come to me and say, oh yeah, I've read your blog and I found this very interesting, or I found that very interesting. So it is a good way of communicating with the community. And now also we have the advantage of, for example, well, we used to have Twitter, that's nothing anymore. But we have the advantage now of Mastodon and Blue Sky and LinkedIn. So I'm using all 3 of these outlets as well to very quickly disseminate small pieces of information. And that gives us a little bit of access to the tools that we need to fight disinformation and to show how science works, and that science works, but also that science is difficult, right? So that's also why I've started using my title again. In my username in Blue Sky. It's not to show that, look, there's a group of people that do research and then there's everybody else. No, everybody can do science, and I would recommend everybody to learn the scientific principles and to understand how they work and how to apply them and how to apply critical thinking. But it's equally as important to understand that science takes a lot of time, and it takes a lot of thought, and it takes a lot of failure before you really understand something. And I don't see the effort into I don't see this effort represented in people who claim they do their own research, right? There's a particular group on the internet which says, oh, you should do your own research. In what I see them do is, well, listen to podcasts. No offense. Listen to podcasts or watch a YouTube video or something, and then think they know something. That's not quite it. You've just listened to somebody else who claims they know something, and then it's up to you to really verify and test those assumptions and make sure that what they're claiming is right, because we all make mistakes. I make a lot of mistakes, and it's very important to take everything I say with a grain of salt and to apply this critical thinking. And you can get training for that. That's what universities are for, or that's what universities are supposed to be for, right? They're supposed to teach you at least rudimentary how to do science, how to do critical thinking, how to write a report, how to document your science, how to communicate this to others, what kind of fields there are, and what information you can get from other fields. So it gives you a foundation which you can then apply to all the other aspects in your life, right?
Yeah.
So I don't think science is really I don't think science is really something you do 9 to 5, right? You either do it all the time, or you don't really, or you didn't really commit to it.
Couldn't agree more.
But that is also super alienating, right? Because
Yeah, of course, of course.
if you talk to your family and you start applying scientific principles to their arguments, they get super upset about it.
I mean, I mean, this is one of the reasons why I started this podcast, because I don't want science to be a black box. And when I talk to my friends, my non-academic friends or my non-natural science friends, they have no clue what I'm doing when I'm in a lab or at an instrument or in a
Yeah.
neutron source or synchrotron.
Even a lot of PhD students don't have a clue about
Yeah.
what their colleagues are. So that this is part of the reason why we get the imposter syndrome, right? Because even as a student, even as a PhD student, you get the idea that your colleagues and your fellow students are so much better than you, because you only hear about their positive results and you only hear about their successes. And that's why LinkedIn, is also a terrible, terrible place, because LinkedIn is full of overly positive posts and overly happy, and you might get the misunderstanding that other people are having lots and lots of successes. No, other people are also having an enormous amount of failures. And it's through those failures that you really learn. And every now and then something works and you understand something. And when you really understand something, then you publish about it. So there's an incredible publication bias, even in things like LinkedIn posts, that gives people a very wrong impression about science.
100%.
So everybody with imposter syndrome, I highly recommend everybody with imposter syndrome to actually follow one of your colleagues in the lab and look at how they do things. Look at how they are experimenting, and look at all the failures that they do, and you'll find out quickly enough that they're doing exactly the same trouble. They're getting exactly the same problems, and they're getting exactly the same kind of failures. Yeah, I always bring up this point. I also give talks about the dark side of science every year, at least once, for students. And this is about some of the things that are not going right in science. Things that lead scientists to commit research fraud. And I explained to them that there are a couple of driving forces to this. One of them is imposter syndrome, so believing that you're not good enough and you need to somehow compensate for this. And the other one is excessive pressure by your managers or by the president or the directorate or whatever you have in your particular institute. Pressure to deliver metrics, number of publications, number of grants, amount of grant money. Those are really the only things that you can measure in science, and therefore those are the only things that these metrics are based on. And that creates a very skewed and very wrong version of science. It means that people are publishing way too quick about way too small an aspect, and we're seeing this incredible avalanche of publications at the moment. Publication rates have steadily increased, even though the number of scientists haven't. And that means we're publishing more and more per scientist, and I can't keep up, right? I'm even in my tiny field, I can't keep up with everything that's published, but also the publications that you read, they promise so much and they try to infer so much from so little data that I can't believe it anymore, right? I can't believe most of the research I read. And when you then try to replicate results, or when you see these reproducibility studies, you actually find that most of the research that is published cannot be reproduced. So what are we even doing, right? that's not science. There's just fantasy. That's another reason why we went into robotics and automation, is to improve
Yeah,
the reproducibility of
yeah,
not just small angle scattering, but also the way that you generate the materials to measure in small angle scattering, because everything matters way more than what we instinctively would think matters. Things like stirrer speed, the stirring bar that you
yeah.
choose, injection speeds, injection orders, they all affect your material.
We had, when I did my master thesis in a chemistry lab, we did
Mhm.
gold nanoparticle synthesis, and
Yeah.
we did exactly the same every time. And the
Mhm.
results were different in summer and in winter because the
Yes.
humidity in the lab was slightly different by a few percent, and this already had an impact on
Yeah.
the seed sizes of your nanoparticles and then the growth mechanism and stuff.
Yep. Yeah, we found the same thing. That's why we did the 1200 syntheses, because they're not
Mhm.
1200 identical syntheses. They're slight changes. Yeah, we found out that if you change the stirring bar from a 12 millimeter ellipsoidal stirring bar to a 12 millimeter rectangular stirring bar, your particle sizes are 50% different.
50%. Wow.
And then if you're just in the lab and you grab a
Yeah.
stirring bar,
Yeah.
right, just one that fits your
Yeah.
vacuum tube or whatever, and you think you're varying one thing between the one and the other experiment, and you go like, oh, well, wow, these particles are completely different because I added compound X. No, they're not. They're not different because you added that. They're different because you took the wrong stirring bar, and you know that makes for very, very irreproducible results. And these are the first things that should be tested and verified before you even think about publishing anything. Verify that somebody else can do the synthesis based on the protocol that you have, that you think you have.
Sadly, I have little hope that the scientists will do this. Sometimes I was thinking maybe I mean journals have by default a pretty good business case, earning a lot of money.
Well, yes.
Maybe they could spend a bit of this money to hire other scientists to reproduce during a peer review process. I mean, not reproduce the entire paper and the entire measurements and data, but
Mhm. Mhm.
just to verify to a certain extent, okay, this is meaningful, this is realistic.
Yeah, I've actually suggested this at some point, that we as a government institute take on this task, right? That we can take a paper
Hmm.
and try to replicate its results. And then when we are able to replicate it, we can say, okay, well, we're able to replicate this, or we're able to replicate these parts of this paper. And when we're not able to replicate, we say, well, this is what we did, but we're getting these results. No blame, no sort of punishment
No,
or
it's just a
aggression or something. It's just,
it
we're trying to replicate this. That's
it's
it.
just the it's just applying the scientific principle to
Yes, yeah,
try to verify or try to not verify stuff and then just put it out there. And what people are doing with this is up to the people, I would say.
yeah, yeah, absolutely. But it's not popular. I think if we change the incentives for the scientists, if we say, okay, um, we no longer count the number of publications that you publish. You're only allowed to put your name on, say, 2 publications a year, whether it's first author or middle author or last author. Think about which project you really want to contribute to,
Yeah.
and then contribute to that project so that you end up on that publication, maximum 2 per year. And that suddenly changes the incentive. Then you go like, okay, well, I don't care about publishing quick. I want to publish something substantial and it really makes an impact and that really
Yeah.
has value. Um,
Probably also not a popular idea,
Also not a popular idea because, well,
especially for people who have very high metrics
that or institutes which rely on
on
numbers,
on the
right?
current incentives. Yeah.
Yeah, exactly. So yeah, well, I mean, I'm good at some things. I'm not good at other things. I'm not good at not good at getting grants, for example. I've managed to get one or two, but compared to the amount of effort that I put into grant writing, it's really low. But on the other hand, I don't really need all that much grant money because as a government institute, we're quite well funded. We're getting a decent amount of money. I'm certainly getting enough money to do decent research with. And I think my time is better spent doing good research than writing grant proposals that have a high chance of failure. But these are the metrics that can be measured, and therefore, if you want anything sort of quantifiable, then those are the things that we'll be focused on. But they miss so much that is important.
Absolutely. And that's why it's so important to speak about this. And this is why it's important to do science communication that, of course, also include these aspects. Because they are part of science, of the science world.
I mean, science communication is also considered a sort of an unworthy effort for a scientist, but I think it's actually super important. Tell any scientist that you're doing science communication, and they think you're wasting your time. We have to teach the public. We have to explain to the public what we do, why it is that we do what we do.
I think it's a certain responsibility of the scientists to not wait for this super slow process, as you pointed out.
Yeah.
The review, and then you have published a paper, and it's not open access, and no one can read it except you pay $40 or your institution has a subscription to the journal.
Yeah, I mean we've seen this during the COVID crisis, right? On the right-wing side.
Yeah.
They were fighting with very rapid succession of information, right? Oh, here's a case where X happened. Oh, here, you know, and they communicate using very fast tools, podcasts, YouTube videos, blogs. And if we restrict ourselves to fighting these very fast things with super archaic, super slow publication methods, then we're sort of we're restricting ourselves. We're hindering ourselves in communicating this. By the time that paper is out, nobody cares anymore.
Absolutely.
So yeah, you need a sort of rapid response team that can actively weigh in on these matters from an educated perspective.
Absolutely.
And show that there's a need for scientists who are more generally versed in a wider range of topics that can address these issues. But it is a lot of effort because you can claim anything on the internet, and as long as people believe it, you win, right? But to make the counterpoint, to prove anything is not the way it is, that is like 10 times more effort.
Yeah, absolutely.
And that is what many people also in the science community stumbled against when trying to combat misinformation on the internet. That it is so incredibly hard to do this well, to combat that idea or those ideas, and that then was exploited as an argumentative tactic, where you can do something what was called the Gish Gallop or sea lioning, where you basically make a quick statement, you put the burden on the other person to prove you wrong, and then very quickly you jump to other topics, or you just give like 10 different things. You go like, okay, well, disprove all of these, because otherwise, if you disprove one of these, I will say, yeah, but what about the 9 others, right? So yeah, those are argumentative fallacies for sure, but people are not trained to recognize argumentative fallacies anymore, and they're not able to realize themselves that this is actually a faulty argumentative tactic. Argumentative tactics should be something that would be discussed. That should be something that should be taught in secondary school at the very latest. How do I critically read a newspaper article? How do I critically listen to a podcast? I've done some research on this, and you can read one book on argumentative fallacies, and you immediately can recognize them in scientific papers, because we're only human. We fool ourselves as well, and that is exactly the kind of thing that we need to train ourselves for, to recognize sooner. Sorry, I think I'm drifting off a little bit
No, no,
on the
it's
topic.
it's super interesting. Also, I mean, these are all aspects that come together when you're a scientist, and these are different perspectives that sooner or later you start to incorporate because you are more experienced. And that brings me to my next question. Now, just imagine you could travel back in time and you're meeting your younger self. How would you look like when you see your, let's say, 10 years younger self? What would you tell him, the younger Brian, or what question would you want the younger Brian to ask you, the time traveler Brian?
That is a good question. I think the younger me was certainly a bit more of a prophet. As in, I used to try to convince people of particular points of view, of particular methodologies, of particular ways of doing things. I would try to convince them that there's a right way of doing things and there's a wrong way of doing
Hmm.
things. This is a right way of doing things, and this is why, and so on and so forth. I've stopped doing that now because most people don't care. They don't have the time to, or maybe if they care, then they don't have the time to implement all of these, or they think that it's not particularly applicable to them.
Yeah.
That's perfectly fine. So the attitude that I've taken now is, well, I can demonstrate that this is a good way of doing things. And if other people want to know more, I'm more than happy to explain everything to them. But if they don't want to know more, that's also perfectly fine. They can do whatever they
Yeah.
want to do. I'm there if they need me, but if they don't need me, then it's also
Yeah.
okay. I think since 10 years ago, I've also grown a lot more cynical about the way we're doing science. Well, maybe cynical, maybe skeptical is the right word, because I can see more of the failures in science. I can see where it goes wrong because I've been investigating this for like 10 years for these talks, right? Um, I can see where it's going wrong, and I can see that it's getting worse. And this worries me a lot, right? We're going down a dark path in
Mhm.
science where we might end up with a sort of facsimile of science, something that looks like science but isn't quite science, right? But we convince ourselves that this is how science is supposed to be done in the modern world or whatever. But it's rubbish, and we need to take a step back and reassess what we're doing in science. And that was actually one of the benefits of the COVID time, because we could take this step back, but people could take a little bit of time and think, okay, what actually really matters to me? Is this important to me, or this whole rat race, or do I really care about something else? So that is also the point where I thought, okay, well, let me just focus on doing what I think is fun and not what other people think I should be doing. Because if I do what I think is fun, I will automatically be more motivated. I will
Yeah.
automatically be more driven and more interested and so on. And for me, it automatically leads to science, right? And if I'm having fun and other people see that I'm having fun and that I'm enjoying it, then they will also have fun. Right? So it's sort of a little bit infectious in the lab.
Yeah, you spark this motivation, this curiosity about a
Yeah.
certain topic. This is how I mean, I never thought that I would do a podcast episode about small angle scattering because
Yes.
it is a very nerdy topic, but I mean, we are talking over an hour now,
Hmm.
and at least to me, it's far away from being boring.
Yeah. Yeah. I mean, well, I also like to talk, right?
Ah, that's
I have I
this
have
is the
many.
format for this.
Yeah, exactly. But I have many sort of things in my head, and they all need to come out at some point, and they tend to pile up
Yeah.
until well, I usually write blog posts about it, but still they pile up, right? Until I write a paper about it, and that's sort of a relief valve, and then from that point on, that pressure relieves, and
Okay.
then I can build up some new ideas. So yeah, first time this was about data corrections. I wrote a whole data corrections paper with like 21 corrections. Then those 21 things were out of my head. That was great. And the next thing was about small angle scattering in more general terms and so on.
Yeah. Yeah.
So this happens from time to time, but it's not. I don't write like publications per year. I write like maybe one first author publication every 2 years or something. It's not quick. Even though there's all these things going on, and even though there's lots of people that come measure in the lab and add us to their papers, because we actually contribute to them, right? But my own research, yeah, that is something that happens at much larger intervals than maybe would be.
So
Mhm.
to sum it up, maybe publish less, but publish more meaningful. Would this
If
also
you
be?
can, yeah, I think this is the benefit of having a permanent position.
That was exactly what I wanted to ask.
No,
Would this also be your advice for early career scientists, first postdoc who wants to
no,
stay in academia and
no,
has not a permanent position yet?
no. That's unfortunately not the way
No.
to get a permanent position. I mean, think about whether you really want to stay in science and really think hard about it, because industry is also not bad, pays a lot better, has a much better work-life balance, even much better career opportunities. So consider it as a real option, and don't fall into stigmatizing in
Yeah.
industry as that's just industry. No, I mean, industry is fine too, and like they're actually offering some decent jobs as well. If you really want to do science, I would recommend spending a few years as a postdoc, but doing so in places that give you freedom. So sometimes you're hired as a postdoc on a particular project, and then you have to do that project. But there are also a few places around where you can propose your own project. And I had one of these in Japan, where, this International Center for Young Scientists at the National Institute of
Hmm.
Materials Science, where you propose your own project and you go and do research for a couple of years on your own project. And there you can really show, like, look, I am able to do independent research. I can make up this whole project and fill it with decent investigations and publish about it. So
Yeah.
those publications are necessarily more smaller in scope, right? And you use that time to make those publications and to advertise those publications, because you really need to bring that out in the world and to talk to
Yeah.
as many people as you can. And that is giving you a little bit of a step up in terms of searching for permanent positions. Now, permanent positions are incredibly hard to get, way harder than they should be. This is partly our own fault, right? When I talk to my partner, she says, "Well, I thought you scientists were supposed to be smart people. So how did you end up in a world where there are hardly any permanent positions?" Because in her line of work, it's absolutely normal that you get a permanent position, right?
Yeah.
You start with a 6 month trial period, and after that is a permanent contract. But that doesn't mean that she's stuck in that one place, because she changes jobs every few years. But it just means that you don't have the absolute requirement to pack up your whole life and move somewhere else every couple of years, because that is exhausting, and at some point you want stability.
Yeah. And in science, you're stuck at the permanent position because there are so few of them that
Yeah,
once you have a permanent position, you don't
you
let lose
hold
of
on
it.
for
Yeah,
dear life.
forever. And this is
Exactly.
then, I mean, should also
Yeah.
not be like this.
No, I absolutely. It's a very caustic environment. So you have to do your best to stay sane and stay healthy.
Yeah.
Really take care of yourself, because nobody else is. Um, don't strive to be that sort of top scientist person, but whatever you do, do it to a high standard, right? Do it well. Make sure you're careful in what you do, um, and that you do things right rather than quick, and so on. So you try to search for the quality in your work. Try to do things in a way that you can trust the results and that you're proud of the publications that you've generated. Yeah, and mostly find ways to have fun in your work. I mean, you're going to be spending so much time on it, so you really need to be happy at work, and you need to be happy with the things that you do, even if that means that you're not necessarily doing things that other people want you to do, right? I'm not saying just ignore your supervisor for everything, right? I mean, they also have things that they need to do and the things that they need to have done. So try and be helpful to them, but don't automatically say yes to everything that comes your way, or everything that they try to push on you, and go like, look, my time is limited. I can only spend so much effort on this. And if you want me to add that, then I have to drop something else, right?
Yeah, no, it's life or science and balance, I would say.
Yeah, no, we are inherently restricted by time and life, and
absolutely,
and we unfortunately can't do everything. I wish we could. I wish I could split myself into 5 people.
Would
do
that
everything
be
that I wanted to do.
Would that be the superpower you're wishing for?
To split myself in 5 people? No, I think I think I would sort of instant teleportation would be nicer.
That's a good one, yeah.
But because then I can immediately go to the beach after this and go and get some surfing in.
A lot of good advices at the end. Thank you so much for joining the show. Is there anything you want to add?
No, I think I've taken up way more of my time than.
Well, I loved how this episode turned out. From nerdy small angle scattering to science communication to dark academia, but then it's an optimistic end, I would say. Thank you. It was a very nice discussion. I learned a lot.
All right. Then,
thank you.
Yeah, I'll go back to the lab and screw around with the machine a bit more.
Good luck with this. Good luck with this. And see you around at
see you later. Yeah.
Conference or Beamtime or wherever.
Yeah, or maybe at a code camp about data corrections.
Oh, maybe this, yeah.
Exactly. All right.
All right. Take care. Bye-bye. That's a wrap on today's episode. Let me know what you're thinking of our discussions about small angle scattering, but also about academia in general. And if you're listening on Spotify, a quick rating helps me to reach even more curious minds like yours. Thanks for tuning in. I'll catch you in the next episode of Your Friendly Physicist and Other Nerds. And until then, stay curious.